So welcome to the HPC Best Practices webinar series. This series is brought to you by the IDEAS Productivity Project, which is part of the Exascale Computing Project of the United States Department of Energy. This series is a collaboration involving the computing facilities at the Argonne, Oak Ridge, and Lawrence Berkeley National Laboratories. I'm Wesley Marquez from Lawrence Berkeley, and will be the host for today's webinar, Managing Academic Software Development. The webinar will be presented by Sam Mangham. Sam is a senior research software engineer at the University of Southampton in the UK. He has an interdisciplinary background. He has worked on fusion neutronics and then moved to the mapping of supermassive black holes. He graduated in 2018, and then he joined the University of Southampton's Research Software Group, where he has been ever since. He's a generalist in his role as research software engineer. He develops web platforms for the art, software archaeology of ancient physics codes, and also helps in the design of machine learning pipelines. He's a trustee of the Society of Research Software Engineering, the UK, and he helps to organize the Research Software Engineer Conference in the UK as well. We have issued plus more than 180 tickets for today's webinar. Let's see how many people join us at the end. All attendees have been muted upon entry. We'll be receiving questions through the Zoom chat and also the Google Doc. I'll paste the address in the chat momentarily. And we have asked Sam to add breaks during his presentation so he can respond to the questions that come in. With that, Sam, I will stop my sharing here and you take over, please.
Great, thanks, Wesley. Okay, so can everybody see my slides?
Yes, sir.
Brilliant. Great, so just move that bar out of the way so I can see my notes. Right, so hi everyone, I'm Sam Mangham and I'm here to deliver this talk on managing academic software development. So yeah, I've already been introduced, but I'll just go over myself again. So quick bit of background, I am a senior research software engineer at the University of Southampton in the UK, as well as being one of the research software engineers working for the Software Sustainability Institute here. And I'm a trustee of the UK Society for Research Software Engineering, or Research Software Engineering rather. So as a software engineer, I'm an interdisciplinary generalist, and as an RSC, I've worked on everything from web-based machine learning platforms to HPC codes for astrophysics. I'm also involved in training and community work. So if you are in or near a GMT time zone, please just ask me about the Society of Research Software Engineering's mentoring program later on, because we are kicking that off soon, and it'll be good to make sure people are aware of that. So my background, though, is pretty solidly in high-performance computing. So I originally worked as a radiation physicist in the UK's National Fusion Labs, the Culham Centre for Fusion Energy, in the neutronics group. So running Monte Carlo simulations of the radiation levels in fusion reactors, tracking neutron-induced activation in materials, that kind of thing. But in addition to working on running simulations and expanding the modelling software, I also worked on developing tools and workflow improvements for the research group. Then I left to get a PhD at Southampton, again working on Monte Carlo modelling of radiation, this time around supermassive black holes to determine how light echoes can be used to probe their outflows, reverberation mapping, if anybody is familiar with it. And as well, because I'm a born research software engineer, I put a lot of effort into trying to get the code documented and tidied up. And also, along with all of the other people working on the code, tried to persuade the professor who had originally written it that it really shouldn't be named Python anymore. But that argument was unsuccessful. But anyway, both these projects were old, large HPC codes. So first in Fortran 77, then in sort of inexplicably pre-ANSI C. So I've got some relevant experience for a HPC talk. But to begin, why am I giving this talk? What do I even mean about how to manage software development, and what in particular is special about it being academic software? So there's a lot of advice on the internet about how to manage a software project. We're probably all familiar with terms like agile or waterfall, but most of it comes from the perspective of industry, developing enterprise software. It's usually calibrated for large teams, working within a formal project management framework, usually with specifically employed project managers. Focusing on kind of how to produce a product to a tight deadline. In academia, things are pretty different. There are more solo developers or small teams. Most developers have limited or no formal training in software development, and most have to self-manage their time. And on top of that, they aren't really employed to produce software to begin with. It's the papers that are the product. The software is just a byproduct. So as a result, a lot of advice from industry is just a bit much. And it doesn't help as well that there are entire industries based on overcomplicating how to manage a project so that they can deliver expensive training courses in it. Of course, so research institutes and national labs lie somewhere between the two extremes of industry and academia, depending on where you are. So those with large, well-funded teams might have a lot more of the kind of formal industrial style project management, whereas smaller groups will tend to more closely resemble the kind of loosely structured environments of academic software development. But regardless of where you are, the sheer volume of material generated on project management suggests it's an important task. So academics typically work on many different projects, all kind of cutting edge and complex with a wide range of collaborators, but with very little training or support in how to manage them. So this talk is intended to provide an introduction to relatively simple, straightforward tools and practices that can help you structure your development a little bit better, hopefully producing more reliable, sustainable software. It's not intended to be exhaustive or prescriptive though, so please take what works from you and what makes your life easier. So I'm going to split it into three main parts, covering kind of the three bits of the life cycle of academic software. So first, I'm going to discuss how to keep the development of the code clear and kind of on track. So how to write the code to make sure it will enable easy development in the future. Then I'll cover just a few tips on how to sort of manage its ongoing use to maximize its usability for you and the community. And then finally put a bit more depth into how you can manage the publication of your software. So you might be familiar with some or even large parts of this, but hopefully everyone will find at least something useful to take away from it. So first of all, I will just kick off with some best practice on how to develop your software. So just to quote at the top, programmers tend to start coding right away. Sometimes this works. That sometimes is doing a lot of heavy lifting there. So a common approach to academic software is just start coding. We know what we need to do. We know how to do it. Let's just get on with it. I mean, this can work for small, simple projects, but for anything substantial, you quickly hit the limits of it. You end up with projects that hit unexpected roadblocks, spiral in size as every new meeting and every collaborator you contact generates a new avenue of research. And these projects quickly become unmanageable messes where nobody really knows what anybody else is doing or how far they are through what they agreed to do in the first place. In order to make our development process more sustainable and more accessible, we need a framework to describe and to structure it. So fundamentally, any project, software or not, can be broken down into a series of discrete tasks. Breaking a project down into a series of small, descriptive and self-contained tasks forces us to think through and define what we're actually doing. So a common tool for doing this is the Kanban board or project board. So you might have already seen them, you may be familiar with them. They're kind of intended to provide a visual depiction of your development process, and they're available integrated into lots of repository hosting sites like GitHub and GitLab, or they're available independently on sites like Trello. They allow us to display and track the tasks we've decided as sort of cards on a board, moving them between things like to do, in progress, and done columns. So this kind of gives us a nice visual indication of where we are. And we can also break down tasks into smaller subtasks when they turn out to be sort of too large or a bit unwieldy. So using a project board gives you a really clear illustration of where you are in the project and what's left to be done on the project. So most sites that manage project boards will also allow you to comment on the tasks that you've created. So you can attach links, pictures, or text. So this allows a project board to function as something kind of analogous to an experimentalist lab book, allowing us to keep running notes on how we're accomplishing the tasks, what problems we've run into along the way, and the steps we took to resolve them. So I've just got a small thread on the right-hand side that shows an example of me working on a, unfortunately, more complicated project than we anticipated to begin with, and a very, very horrible entity relation diagram. So it's kind of important to keep this clear documentation of your development process. There's kind of the concept of the bus factor in coding. How many developers on a particular project would need to be hit by a bus in order for it to become unrecoverable? So for most academic software, the bus factor is 1. If that one developer becomes unavailable due to illness, or they leave academia for industry, or even they just lose funding to work on the topic that they are working on, what you have left over is a kind of incomprehensible mess with a sort of undefined amount of work that's left to do. Without clear task management as well, it's also harder to collaborate with others. So, bringing a new PhD student onto the project involves kind of having to dump a vast amount of context and information from your head into theirs. And keeping track of the progress and the problems that have come up along their way then requires endless meetings between you and them. It's also a problem if you just kind of step away from the project, as in many ways, future you is just another collaborator. So a huge amount of knowledge can decay in a short amount of time whilst you work on another project. So documenting the state of development when you left it makes jumping back in later on a lot easier. But one of the main problems with using project boards in academia is, unlike in industry, the initial scope of our projects is often very poorly defined. And also, academics are, if nothing else, generators of ideas. Any attempts to do anything will inevitably turn out to be far harder than is expected, because this is cutting-edge research. And it will also spawn several ideas for new papers. It's far too easy to end up kind of overcommitted. So with too many unfinished, sort of half-finished features just lying around on your code base, with a project board that accrues tasks faster than you complete them, and everything just kind of gets trapped in the in progress column. So the best way to avoid this is to kind of prioritize and scope your project, which we can do by borrowing a few techniques from the agile methodology used in industry. So there's plenty of guides for full implementations of the agile workflow, but as mentioned before, they generally rely on a much more structured work environment than we have, often with things like formal project managers and roles like product owner that don't really exist in academia. So it's a lot easier for us to kind of pare it back to just what fits our needs. So if we're using project boards to track the individual tasks that make up our project, we want to try and come up with rough estimates for how long each task will take. Once we have those estimates, then for a given block of time, which in industry, they would probably call a sprint, but in academia, where our schedules are messy, clogged up with teaching and conferences, it might end up being like a month or two. We want to take that block of time and fill it with tasks of sufficient length to fill the development time we have available and kind of prioritize them. So a common strategy for this is Moscow prioritization: must, should, could, and won't, where for a given block of development time, only 60, touched my space key whilst I was doing hand gestures there, where for a given block of development time, only 60% of that is supposed to be on tasks that we think are essential to the project. So however long you're going to make this block of development time, about 40% of it should be on things that just aren't essential. They're sort of features that maybe your code should have, but you can live without. They're things that you could fit into the paper, but you can publish without. So that way, if or when our time estimates turn out to be wrong, because they will inevitably be wrong, then instead of kind of dragging the task out forever, you already know, you've already decided what to drop. So instead of dragging the task out forever, you can decide, well, we'll only compare 3 different algorithms for the code rather than 4. Or we'll drop support for a particular input format, or for a particular physical regime. But crucially, though, an important part of prioritization is acknowledging upfront what you won't do, what's out of scope if you want to have a hope of finishing your code before a conference or of getting a paper out in the next 6 months. But we keep those won'ts around to do later. They're not gone forever. So then after you spend a month or two, working on this code, as your tasks turn out to be, large, get broken down to subtasks, you kind of reconsider the importance of the various parts of your code, new ideas bubble up, you kind of take stock, you reprioritize, and you consider the work that you'd like to get done in the next couple of months. So that might not work for your project. It might be that you genuinely can't think of any parts of your code or of your project that aren't completely essential, and you may not have any strict deadlines. So it might genuinely be a matter of it's done when it's done. But even then, it's still a good idea to take a leaf from Moscow prioritization and assume that the estimate of how long it will take is probably, going to increase by about 2/3. But so yeah, as mentioned, when you're setting up a project, it can be hard to decide what is a won't. Like generally, we do still want to accomplish all of our ideas, right? So the won'ts aren't forever. They're just for the current chunk of development. So for a typical academic project, they're likely to include potential avenues of research that open up during the project, but you didn't budget time for. So if you don't prioritize by explicitly allocating these things to the next paper, you will often end up trying to cram them into the current paper. And as a result, that even if you do fit them, the paper will often turn into kind of a sprawling mess that you end up having to split into 2 parts anyway. Other typical won'ts come from collaboration, for example. So it's a common problem to want to satisfy all of the feature requests and all of the bug fixes that your colleagues and collaborators, want just straight away. But this spreads your time much too thin. And inevitably you end up with your project turning into a game of whack-a-mole, where you just kind of work on the thing that's the last email you got was about. If you don't have the time, then it's just better to be upfront about that. Just let people know that a particular mode they want isn't coming for a few months, or that a bug that affects a particular, regime, physical space, or a particular parameter set they want to explore is just too gnarly to fix right now. It's just not on the to-do list. So this lets people plan their own projects better, instead of things like having PhD students just spinning their wheels for months, waiting for fixes that won't be coming anytime soon. Or, bombarding you with emails asking you, when is this feature going to be completed? When you just know you don't have the time for it. And as well, sort of just trying to cram too much in, and poorly prioritizing and overloading a project with new features will often result in important parts of it becoming neglected. So it's common to end up publishing academic code that's packed full of interesting and powerful functionality, but doesn't have any tests to prove it actually works, or doesn't have any documentation to allow anybody other than the developer to use it. So nobody in their right mind would suggest upfront that code should be untested and undocumented. So when you make that acknowledgement part of your development process, part of your task allocation and prioritization, that ensures that these essential things don't just fall by the wayside. So just a quick slide on version control. I'm assuming everybody's code's already on version control. If your code isn't, please just stop watching right now and get it set up. Version control and remote backups are absolutely critical to good project management, not least because if your building burns down, as Southampton's computer science department did in 2005, and you can see from these delightful pictures, you will continue to have a project. You will not just have a pile of ash and tears. So in addition as well, having a continuous record of the state of your code is vital, allowing you to easily test the differences between different versions of the code, identify where unintended changes to behavior or code have snuck in, as well as being key for publication and reproducibility. Being able to roll back to the version of code you use when generating a paper to respond to a referee's request for revision is kind of key to avoid ending up with papers that either contain a mishmash of results generated by different versions of the software, and thus the validity of it becomes a little bit questionable, or constantly redoing the analysis in your paper every time you get a sort of a new change, which wastes a huge amount of time. So that aside, obviously I'm assuming we're all in version control. One of the key features that version control gives you for project management is the ability to have parallel branches of code. So common branching version control workflows are to have a main branch containing the stable version of your code that you'd like to share with users, that you published papers using, that kind of thing, and a development branch, which is used for your work in progress versions. So this model works particularly well with the kind of task-based, board-based project management styles we discussed earlier, because then instead of trying to implement every single task on the development branch, you can easily parallelize. Each task that would take more than about a commit to do can be implemented as part of a new branch. You can isolate it from the others, making it far, far easier to implement and test that one particular feature without the risk of accidental bleed over into it from other changes to the code. If a task turns out to be more complicated than expected, or it stalls because in order to execute it, you need data from collaborators that they haven't provided, or because your tests take weeks to run, you can then just, instead of being stuck and spinning your wheels, switch to a different branch, work on that one. And also it makes it really easy to collaborate because, of course, each individual developer can work on their own branch, and then you can easily kind of fold those things together. So ideally, the process of merging these branches together into the development branch will happen once they've been, rigorously tested. And ideally you can sort of, oh, I'll get to that a bit later. Yeah. And then so once you've managed to sort of merge all the various new features into your development branch, once you start using that in a paper, then you can use that to merge that into your main and sort of create a commit for that. So it's important to keep the scope of branches contained and to regularly merge them back into the development branch. Or if the branch is going to be long-lived because development is very complicated on this feature and it's going to take a long time, or because the tests are going to take a long time, it's important to then at least routinely pull the development branch into it to keep it up to date. So one of the common pitfalls of this workflow in academia is individual researchers end up making all of their changes to one branch that they own. And then that branch ends up so far behind the rest of the code that they just don't have time to merge it back. And you end up with entire projects worth of work becoming marooned in divergent branches that nobody just has the time to fix. So a common practice in industry, and one that you can even adopt in single developer academic projects, is to make these merges, hopefully, regular merges of well-scoped amounts of work, as formal pull requests. So sites like GitHub or GitLab provide interfaces for these, where you can set specific procedures that have to be completed before, when a merge is requested, but when a pull request is raised, but before the branch gets merged in. So ideally, this would include things like getting collaborators on your project to peer review them, as well as doing things like running tests, making sure that documentation is up to date. But even as a solo developer, this branching workflow and setting up formal pull requests means that you have to stop, take stock, and kind of go through the checklist of things I should have done. Have I remembered to do them? So that's kind of like an important thing that's added to your workflow. But so that's all just kind of project management stuff. But we also need to consider how the code that we write factors into the long-term management of our project. Not just the kind of the meta level stuff. So poor or idiosyncratic code is very hard to maintain. It's hard to share, and it tends to lead to a buildup of technical debt that's hard to address. Your decisions become opaque. It's sort of hard to understand why you made a particular decision, and it gets increasingly hard to change that decision afterwards. So you might not consider it worth the effort if your code is only going to be kind of a disposable, single writer, single user project. But code always tends to be more reusable than that. One of the main problems with academic projects is how simple codes that are kind of slapped together as a proof of concept inevitably become the foundations for larger ones. And that then undermines the long-term functionality of the large code. So it takes a lot more effort to correct problems once the code has grown than to fix them early on. And if you don't do those fixes, your code will eventually reach your project will eventually reach a point where, through years of PhD student and postdoc churn, nobody really understands how it works anymore. And the only practical solution is just give up, rewrite it from scratch. Plus, as well, the idea that any code you write is a single user project that nobody else will ever read or run is kind of assuming that your research is irrelevant. If your code generates important results, people will want to be able to understand them and should be able to replicate them. Plus, also, even thinking selfishly and in the short term, even if this is still a single developer project, that developer is very unlikely to have a perfect memory. So unless you can guarantee that, for example, you can remember every single quirk and decision that you made when writing your code, it's worth, just putting in a little bit of extra time to make sure it's readable, so that, in 6 months down the line, when reviewer 2 asks you an awkward question about something, you kind of remember why you made that decision without having to spend days picking through opaque text. So the HPC BP seminar series has previously covered sort of advanced techniques for reducing technical debt and improving sustainability, so like containerization. But in this brief section, I will just focus on just code design itself. So odds are you will already be doing a lot of this, but So fundamentally, for a properly managed, sustainable project, your code should be as readable as possible. The more human readable the code is, the easier it is for you to expand the project by bringing additional collaborators, and the more sustainable it becomes. So, as mentioned, academic software will often pass through a chain of new PhD students, and onboarding them is always a time-consuming and complex process. If your code is full of shortcuts and quirks and idiosyncrasies, this encourages the students to develop and add idiosyncrasies of their own. And future development then quickly becomes bogged down by the complexity of understanding what exactly did the last person to have their hands on the code actually do? And is that what they meant to do? Because, they might be a fresh PhD student. So the best way to avoid this and to keep your project clear and comprehensible is to stick to a clear coding style. So most languages will have different style guides that define conventions of things like spacing, braces, name formats, that kind of thing. The specific choice is generally just less important than picking one and sticking to it. And also, if no existing style is entirely to your taste, there's always a temptation to declare your own coding style. But by using one that's publicly defined and widely adopted, you reduce the mental load on people joining your collaboration. And it makes it easier for people to get started on your code, which means that you get more science done more quickly. So checking style compliance is a common feature of linters, static code analysis tools available for most languages. In Python, PEP8 is the main community standard that's checked by a variety of linters, including things like PyLint and Flake8, while C++ has things like the LLVM style set you can check against with Clang Tidy. There's also even more aggressive code formatting tools like Black for Python or Clang Format for C++ that automatically restructure your code to fit a specific style, so you know that that's been done. So another major readability boost, and one that can't be automated, is choosing clear descriptive variable names instead of the classic single letters like A. So this might make it quicker to write your code, and in many cases it will then more closely resemble the equations that you're modeling. You will quickly run into problems as sort of name collisions as your code grows and adds new libraries. Short names become ambiguous and confusing at best, or actively clash with other variables and functions at worst. Refactoring to avoid it becomes a pain. And again, the code becomes more dependent on human memory. In order to, as the code grows, you have to have an increasingly large list of things you need to remember off the top of your head in order to be able to contribute. So fortunately, most integrated development environments like C-Line or Visual Studio support automatic linting. They point out violations of code standards, as well as things like auto-completion that make long descriptive variable names just as easy to use as short ones. As well, I would recommend using proper IDE because they have the functionality to mount remote file systems, which simplifies development on HPC. And code is also a lot more sustainable and readable when modular, right? So breaking code down as far as possible into sort of small, well-defined functions with clear inputs and outputs makes for much easier development. They more naturally fit into the task-based and feature branch workflows. They're kind of easier to work on in parallel, and it's generally just easier to refactor as well. So when you need to modify the structure or functionality of your code to enable future expansion. So this last bit is a key point. No code will ever survive a long time without needing refactoring at some point, because your initial design cannot possibly take into account all the possible future uses you might want to put your code to. So if you have code with clear descriptive variable names contained in sort of small, well-defined modular functions, it's really easy to restructure your code base without having to make extensive edits to the code itself. And also, so even the most human readable code is not completely obvious to the reader, no matter how hard you try. And so that means most projects fall foul of the bus factor. So we need to ensure that the context and justification of our code lives somewhere outside of our head, again, to enable us to bring new collaborators on board and to protect ourselves from the inevitability of knowledge decay. So if you've written your code in clear, descriptive, human readable modular blocks, this should actually be quite straightforward. We just need to document what we're doing and why, but without delving too deeply into the mechanics of the implementation, because they should be clear from the code itself. In actual fact, you can, taking this into account, you can write the documentation before you write the code. You define what the function does, what it takes, what it returns, and then you make the implementation. You can even take this further to something like test-driven development, where you define the tests that your code would need to be able to pass in order to actually do the functions that you want before you write the code. So if you do it in this way, it's much easier to kind of expand and extend your software, as the functionality is kind of clearly exposed to you, not sort of buried in dozens of lines of code. There's sort of community standards for writing comments that allow them to be passed by documentation tools like Sphinx or Doxygen. So these extract comments from your source code and compile them into API documentation intended for developer use, stuff that's easily searchable and a major time saver. So then websites like Read the Docs or codedocs.xyz will allow you to link up to a GitHub repository, and they will automatically generate the documentation for it using one of those tools, and then host a web page for that documentation. And once you have these web pages, they make your life just so much easier. Even experienced developers in a project will find it easier to kind of search a website than rack their brains to the location of a function in a kind of increasingly sprawling code base. They can even generate call graphs, so illustrating which functions call others, allowing you to easily understand the structure of your code. Particularly important when other collaborators begin to add to it. So I've included a simple example here from a non-scientific project, as unfortunately, the graph generator of the code I wanted to demo has broken in my absence. This also illustrates one of the common problems with documentation. It can go stale. Particularly with large, complex HPC codes, outdated documentation can be a huge problem. You can, and I have, end up wasting days attempting to use features or compilers that are documented as being supported, but have long since been deprecated. And you'll be certain the whole time that the feature is supposed to be working, so it must just be a mistake I'm making. So one of the developments that's intended to counter this is the kind of docs-like code workflow, where you store the documentation for your code and your features kind of as close to it as possible, and you say that documentation has parity with code. Whenever you edit your code, you edit the documentation to update it at the same time. You don't merge branches with, undocumented changes that you'll write up separately later. Of course, this is a lot easier to do in an environment where you have somebody else reviewing your pull requests to keep you honest. And I briefly mentioned test-driven development on the last slide. I'll just skim through it as I'm already running a bit slow, just can't do it justice in this talk. There's a variety of tools designed to make writing code based around tests easier. And a common setup as well is continuous integration, where you write your tests and you use a test framework to run automated tests on your code before you merge branches together. So most sites like GitHub and GitLab will support continuous integration, and many will even allow you to hook up remote computing resources to them in case the resource they provide is not sufficient for your large or complex code. Okay, so that's the first but by far largest section. So I'll just go for the questions then for a bit.
We are clear. Please continue.
Oh, no questions. Brilliant then.
Not yet. No, there was a comment there, but I think it's just the participants liked what you said. So yeah.
Yes. Oh yeah. It also saves you the trouble of writing the documentation yourself. Yeah, this is the big advantage of automatic, well, anything generation. Okay, so the next section then, managing usage. So I've covered how to manage the development of your code to make it as easy as possible for you to write, to keep your development process on track and to make sure that it produces code that is easy for you to work with in future. But how do we ensure the code is easy to use? How do we best manage its sort of ongoing usage in a way that maximizes the amount of actual results that our code can generate? So the first and biggest point is to just loop straight back to documentation. So we've discussed developer documentation of how the components of the code work already, but equally important is the user documentation that describes to a user how to install, run, and analyze the outputs of a code. So a lot of academic codes lack this. The information on how to use them just lives within the brains of a research group or a small community. Getting a new user, like a new PhD student in, involves kind of personally walking through how do you set it up? How do you use it? For anybody who doesn't have, direct connection to this group, who wants to download and use the code, so somebody who's kind of hoping to start collaborating with you, they just have a swathe of unknown unknowns. Are there sort of physical regimes in which the code's outputs aren't meaningful? That's probably the case, because no code is perfect. No code can occupy a whole, parameter space. How do you set the input parameters properly? What are the sort of the common pitfalls that end up making it inefficient or poor quality? So getting this information from the code itself kind of requires knowing where to look for it in the first place. So it's just not practical. So if we want to maximize the usage of our code, and as a result, our contributions to our field, we need to ensure that the code is as clear as possible. We need to ensure it's as clear as possible how to use the code. So fortunately, I've already introduced documentation platforms like Read the Docs. These can include not just auto-generated API documentation, but you can also include handwritten text like descriptions of input parameter files, input file parameters, images, equations typeset in LaTeX. You can even include entire Jupyter notebooks. So for example, this the second picture on this slide is a Jupyter notebook imported into Read the Docs. And you can use those to give examples of how the code is run and how the output data is analyzed. Whilst it might seem like a large investment of time to write that originally, it then saves you a huge amount of time later when introducing people to the code. And on top of that, it involves you documenting features of the code that you're probably going to need to reference in papers anyway. So it's kind of a resource of text for you to mine later on. So yeah, on the right, there's a couple of examples of using Sphinx and Read the Docs to render a Jupyter notebook with a walkthrough of how the code is used, and some documentation on the settings for parameters and how to use them. But you don't have to use a site like Sphinx. You can even just use GitHub Pages to create a documentation on, this very closely links to your repository that holds your code. Or you could create a wiki on GitHub. GitHub supports wiki, so you can just document all of your code there. In general, the easier your process of writing documentation is, and the closer your documentation is both to your code base and to where people find your code, the better. The important thing is we just kind of want to reduce as far as possible the friction required to use our code, which increases its usability, which benefits the field. So another major help for users is having a public record of the issues with your code. So again, ideally, very accessible on whatever repository hosting service you're using. So fundamentally, there's only a limited number of things that can go wrong with code, despite the fact it often feels unlimited. Having a public searchable record allows users to solve their own problems by comparing them to previous ones. Sites like GitHub and GitLab enable this by allowing you to link together issues, making this process easier. And again, the easier it is for somebody to fix the problems that they have with your code, the more likely they are to use it, the more likely they are to cite you. Crucially, though, they let you keep an accessible record of the things that your code can't do, the unfixed bugs, the things people have tried and failed to do with it. So by keeping this open, you can save a huge amount of time spent by people trying to use your code for things that others have already established it can't do. People can be a bit iffy about what they might think as showing their code's dirty laundry, but the benefits far outweigh the cost. And this is especially true if the issues are accessible from search sites. So the traditional paste your error message into Google programming technique works. Because you can't necessarily rely on the people using your software knowing where its help site is. It might have been added, sort of integrated into a larger pipeline, for example. But really, one of the main advantages of issues is that they open up a dialogue with the users of your code. This is valuable even when there's not even that many users, or when the issues they raise aren't actually genuine problems, they're just misunderstandings. Understanding how people are trying to use your code and the things that they want to do with it give you information on what would be useful for you to develop your code to do going forwards, will be, what the field is trying to accomplish. And also tell you, what about your code is unintuitive or inconvenient. Addressing these things will generally kind of improve the quality of your software. That said, it is a lot easier when the issues are communicated to you in a coherent way. And people have a bad habit of not describing their problem in detail, just proposing a change that they think will address the symptoms that they are seeing. Most repository hosting sites will allow you to set up issue templates that encourage users to report their problems in a structured way and make them attach sufficient information to help you debug them. I mean, often just providing a descriptive issue template that forces people to go through in a kind of a systematic way results in them solving their own problems because they've had to think more systematically about what they were trying to do. So yeah, that's the short section on managing usage rather. Anybody have any questions about that, or? Still no.
Okay, now let me see here, the Google Doc. I don't think so.
No, that's right then. Either I'm saying things that everybody already knows, or it's just
Or you sound very convincing.
that's good. So let's move on to finally then the managing release section. So one of the most important parts of developing it's okay, I don't do all of this myself. This is why I was saying, like, it's all about taking and using the important things. It's more of like having a library and reminding ourselves what we should be doing, even though we never actually manage it all. So yeah, one of the most important parts of developing a code is releasing it. So whilst it's common to keep the code internal and to only share its outputs, increasingly many journals are moving to require public release of code. So it's in both our and the field's interest to release it. So I'll just introduce a few ways to manage the release process. So by this point, the vast majority of research depends on software. So a survey in 2014 by the Software Sustainability Institute showed that software was fundamental to over 2/3 of research. And obviously within the field of HPC, it's 100%. But the actual acknowledgement of software as a research product itself, separate from the papers that are produced by the software, is often lacking. This lack of acknowledgement then leads to funding difficulties. Code can underpin entire fields, but just go completely unfunded and rely on kind of maintenance squeezed in around a developer's day jobs, as in the XKCD comic we've seen before. So there's two common outcomes to this sort of lack of acknowledgement and lack of funding. So the first is paperware, just kind of poorly documented software that's riddled with technical debt, just unmaintainable. So rather than serving as a platform for future development, paperware then just gets thrown away and rewritten the next time a new PhD student comes along. This is a massive waste of time and effort, and it's a real hit to research outputs. So the other outcome of this is postdocs who have spent years maintaining vital software finding themselves pushed out of academia by a lack of a publication record. I think we all know at least one person, almost certainly more, to whom this has happened. They often go on to make a lot more money, but that's not good for the science. So yeah, the research software engineering movement is trying to improve this by pushing for greater support for software development and for providing roles for dedicated software developers, but it can only be successful if we publicly acknowledge the value of software. So if you release your software and cite it in your papers, you acknowledge the effort that's gone into it. More than that, you make it clear to others where they can use your software, how they can cite it. So this, again, is essential from the perspective of reproducibility. The software is a fundamental component of your paper and required to reproduce your results. And also, releasing your code for others to use drives collaboration, gets you more citations, and just helps the field accomplish more. So getting other people to use your code can be a bit controversial, because some researchers will shy away from public releases because they're worried about being scooped. You know, other people will use it to accomplish something that they wanted to. But realistically, encouraging others to use your code means you have a head start over them. There is a reason that every tech company obsesses over creating a new standard or a new platform that they can then force others to use. As well, you will always have more ideas than you can implement. So, you know, letting other people do them is not really a big problem. So just cover quickly a couple of tools and practices for managing your releases. Just citing your software by its name will run into issues. You know, it's with reproducibility. As your code evolves over time, the behavior of it can change dramatically. So just saying, you know, we did this analysis with AstroPi is unhelpful. It's like referencing a methods section from another paper that is constantly being rewritten. But fortunately, there is infrastructure in place to manage that. So giving your code a formal versioned release that's associated with a particular paper or a particular output allows you to link that particular version to the results. So in a feature branch workflow, like I mentioned in the section on managing development earlier, these would typically be, these versions would be associated with a commit to the main branch and tagged with a version number that provides a kind of a nice, easy human readable reference, not a commit ID. Sites like GitHub support that by listing releases with sort of a bit of documentation for the release as well. And they also allow you to add a citation.cff file. So that's a community developed file format that provides instructions on how you'd like your software cited. It includes things like linking to your ORCID, Open Research Already, requesting multiple citations. So for example, requesting they cite a release paper and the DOI for your specific version. And also, while get those DOIs, most university libraries can issue DOIs, but Zenodo is a really useful service. It's a website that generates DOIs automatically. If you link a repository up to GitHub, it will provide you with a DOI for commits to specific branches. There's a bit of an annoying chicken and egg situation there where you cannot include the Zenodo DOI for a commit in the commit itself, but they are trying to figure out ways around that with GitHub. But yeah, and also just a bit of HPC specific stuff. When you are creating a release for HPC codes, it is very important to document all of the requirements to run the code, including things like the libraries you use, the versions of them, the compilers you use, and the versions for them. So for heavily optimized code, it's not uncommon to end up with it bound to specific compiler versions. And if this isn't documented, then that's an absolute pain for you to find out. And I have wasted a lot of time trying to do that. So the easier you make it for others to run your code from a release, the more likely they are to write papers using that code, the more scientific outputs they'll produce, so the field progresses further, and the more citations you get, so the better for your career. And just one last thing, I've got quite over time. So when you're making a release, you need to consider the license that your code is under for it, because that can have a major impact on how your code is used in future and even how your development can go. So I'm just going to give a quick overview because the HPC Best Practice series has an entire previous talk on licensing. So without a license, your code is just under whatever copyright laws your country has. So in the UK, the US, and the EU, that means that nobody else can copy, modify, distribute, or potentially even use it. That's yet to be tested in the court of law, I think, even if the code is publicly available. So a lot of academic projects get away like this, but it's kind of like playing chicken. Without a license, then it will usually be your employer who owns the code that you have created and has all of the right to it. This can represent years of your time, and there is always the possibility that if you move institutions or fall out with the wrong person, you might find yourself permanently locked out of the code that you developed. That's unlikely, but I have seen it sort of be avoided by preemptively selecting an open source license, because that's your only protection against people deciding to be difficult. As well, if you don't select a license, that basically prevents your code from being adopted by industry, and you don't get any impacts that way. Because no business is going to sort of risk the legal fallout of integrating like a complex and valuable piece of code into their business practices, only to get a knock on their door several months later from a hungry university that's demanding money. So the other end of the spectrum, there's open source licenses that give others the right to copy, modify, and distribute your code, but without any assumption of liability. So these come in two flavors: copyleft, that require any future modifications to the code are also open sourced in copyleft, and permissive licenses that generally don't require that. It's just, you can do whatever you want, but I don't have any liability for it. So copyleft, unfortunately, also deters industrial collaborators, because if they want to modify your code in order to work with things like internal data pipelines or internal data sources, those modifications have to be publicly available, which means they end up leaking commercially sensitive information. So if there's a risk that your code might be used by industry, copyleft licenses like GPL3 can be a bit iffy. So yeah, as mentioned, technically you might not own the copyright to your code, and you might not be able to open source it technically without working with your university's IP management team. However, at least in the UK, many of them aren't really aware of the realities of academic software development and don't have a good grasp on software licensing. So unless you are looking for a sort of a proprietary license that's custom written so you can charge industrial users, it's easier to just go with MIT or GPL. The consequence, you're very unlikely to face any consequences beyond, maybe, oh, well, maybe you should have asked us. So yeah. And also, if you are thinking of having a custom license, realistically, complex and burdensome proprietary licenses that involve months and months of expensive legal wrangling will also deter collaboration. So if you want your project to have long-term support from industry, doesn't require it. Well, I've seen copyleft only requires source code when the software is distributed, but doesn't require distribution. But that kind of, it depends on how you end up defining distribution, and that's a iffy legal thing, right? Is copying your copyleft code to another computer within your company distribution? I know that there are things like, there are potentially ways around copyleft, and there is the GPL version 3 Affero license, which tries to hammer close some of those holes. But yeah, so if you want your project to have long-term support from industry, it's generally best to just open source it and encourage external contributors. But in any case, licensing is a very long and complicated topic. So yeah, I would recommend chooselicense.com for a straightforward guide to it. And that's it. So that's been my summary of how you can manage your academic software development in a way that will hopefully result in releasing more organized code that's easier to use and get credit for. Thanks for your time, and I hope there's been something useful in this talk. If you'd like to contact me, I wear a lot of hats, but my Southampton email address, s.mangham@sutton.ac.uk, is the best bet. I'd also like to plug a few things as well. So if you're on or near GMT time and a member of the Society of Research Software Engineering, which is the UK body that anybody around the world can join, our mentoring scheme is open for applications until the end of the week. So if you are in the UK, the Southampton Research Software Group is also recruiting. We have posts open for 2 regular RSCs, 2 senior RSCs, and a senior HPC specialist. So it's a great group to work for. So just come join us. But other than that, thanks for your time, and I'm happy to answer any questions about code release or any other topics mentioned in the presentation.
Thank you, Sam. Very nice. So then now I'd like to invite the participants to unmute themselves and talk directly to Sam. There are some comments, good comments in the chat. People can then, as I said, unmute themselves and talk to Sam directly. So I see a comment here in the chat. There's about the spec, about the developer or developers giving presentations at the SC conferences. We also had a webinar in this series about spec some time ago. People like to check previous webinars that we have offered. Any questions for Sam?
Like it?
Oh, yeah, sorry, yeah.
Well, that's
So,
okay.
yes,
I'm actually kind of surprised that nobody has took issue with the most controversial thing I thought I wrote, saying don't have your variables be named like A or B or C or what have you, because every academic code is littered with that. But yeah, that's the thing I always try to kind of hammer in talks. I don't think it's a fight I'm ever going to win, but
there is a question there for you now in the chat,
yes.
Sam, if you can see it.
Softwarecarpentry.org. Sorry, you've seen a few researchers consult with it. So I'm actually involved with software carpentry as a instructor and as a materials developer. When you say consult, sorry, what do you mean? Because I'm only involved with what the UK branch does. Oh, to learn to code. Yeah, I would strongly recommend software carpentry courses, particularly if you are if you have like new PhD students joining, Software Carpentry offers really good introductory courses. And it also is recently rolling out intermediate level software development courses, which go into more detail on things like object-oriented design, like procedural and functional models of code, which go into just a lot more depth around how to design and write higher level, higher quality code beyond just kind of the introductory stuff. There's also loads of courses in the incubator that kind of introduce all kinds of different topics. They're particularly for different fields. There's like machine learning ones. There's ones that focus on geophysics, that kind of thing. So I would strongly recommend Software Carpentry. Probably the people here would have already basically know enough for like can probably skip a lot of like the beginner courses, but there's the intermediate material I would strongly recommend, and not because I wrote a bit of it, but there is some overlap between this talk and some of the intermediate level materials. So yeah.
So Sam, Jorg has a question there for you.
Yes, Jorg. So using software management tools like EasyBuild or SPAC, would that be sufficient to make software installation reproducible? It's one of those things like saying you could install software with a Docker image or something. I think it's good, and it's something you should do, but I would also make sure that you document how you would install it manually. People who just want to use your code will have a much easier time if, yeah, they can just use SPAC or EasyBuild or something. Bam, I have some code up, it's running. But that's not necessarily long-term sustainable, as these tools, the sort of the structure and their behavior will often change over time, and you might end up with your code bound to a particular version of the various easy installation tools. At which point it's then like, okay, well, so I would try to make sure that there is a human readable descriptive version of how to use it, and not just rely on easy installation tools, if that makes sense. But obviously they are a good thing.
Any further questions for Sam? If none, thank you, Sam. Thank you all for joining us today. I'll just quickly here put in the chat, announce the next webinar. I'll just stop the recording now.